Hi everybody, welcome back to Dave's Math channel. I'm your host David Tare, and this is my continuing feature on the Math Lovers book. A couple of days ago I started a new chapter on group theory, and this is my third lesson on group theory, and I'm talking about finite groups, which is section 6.2. And group theory is a very broad topic. I'm going to talk about a lot of different kinds of groups, but today I'm going to talk about a particular type of group, namely additive modular groups, and I'm going to talk about modular addition in particular. So anyway, let's begin. So what is modular addition? Well, it's not really that hard, I don't think. You learn modular addition when you learn to tell time. So just think about the hours on a 12-hour clock, except replace the 12 on top with a 0. And then just add the way you would add hours. For instance, if the sum is less than 12, you don't have to worry, like 3 plus 5 is 8. But what about 7 plus 6? Well, 7 plus 6 is ordinarily 13, but we have to take the remainder when we divide by 12, so that gives you 1. And of course, you know that 7 hours after 6 o'clock is 1 o'clock. So it kind of gives you the addition of hours on a clock. That's one way to think of modular addition. So anyway, and the modulus doesn't have to be 12. It is for a clock, but the modulus can be any positive integer you want. Doesn't even really have to be an integer, but here we're looking at integers. And in this group, I'll get into this later, but this is a cyclic group that I'm describing here. This is the group C12. It's isomorphic to the group we talked about, I talked about yesterday, cyclic group of order 12. Anyway, let's just continue here. So here's a picture of it in the middle of this slide. They say a picture's worth 1,000 words. And I took this picture from the web. This picture isn't in my book, although I probably should have put a picture like this in there, I guess. So here I'm just kind of specifically showing you what this group looks like. This group, I'm calling it G here, but it's really the additive cyclic group modulo 12. And I just showed you how it worked. I don't think I have to say too much more about it. But anyway, and another very useful thing you can do with groups, they don't have to be modular groups, but groups in general. There's something called the Cayley table of a group. And this is like, you can think of it as a multiplication table. In this case, it's an additive table. Remember, group multiplication doesn't have to be ordinary multiplication. A lot of times it's addition. As a matter of fact, when we're dealing with cyclic groups, it's usually easier to think of them as additive groups, where your group multiplication is addition modulo n for Cn. In this case, when n is 12, our Cayley table is just a table of addition modulo 12. And this is how you add modulo 12. It's a table. You probably saw regular addition tables when maybe in first or second grade when you were learning how to add. Here you're doing pretty much the same thing, except you're taking the remainder when you divide by 12. So every time the number is bigger than 12, you just subtract 12, basically, greater or equal to 12. So that's what the addition table, the Cayley table of C12 looks like. And like I said, we're going to see a lot more Cayley tables. Cayley tables are very useful in every group. I guess every finite group at least has a Cayley's table associated with it. If the group's really big, it might be too impractical to make one, but for smallest groups, Cayley tables are very useful. So anyway, now you saw a Cayley table. And what else can I say? We didn't prove this thing's a group yet. I mean, it is isomorphic to C12, but I'm going to prove that later. First, just to see it's a group. I mean, just imagine somebody told you that, we're defining this group, C12 of addition modulo 12, and they told you the rules. And now, how can we prove it's a group? Well, we have to check each of the 4 axioms. And first, I'm checking I guess I'd check, associativity. I mean, probably, closure is obvious, right? Because, I mean, if you take any two numbers from 0 to 11, and inclusive, and you add them, and you take the remainder. When you divide by 12, you're always going to get another number in this group. So that proves that it's closed. What about associativity? Well, you could do a little trick here. This is a little bit of an algebraic trick, but we know that ordinary addition is associative. So what happens when you do ordinary addition and then you take everything modulo 12? Well, I think it's pretty easy to see that, since ordinary addition is associative, it doesn't matter whether you do them, take things modulo 12 before or after you group the terms. So if you group the terms first and take it modulo 12 and then you add, so for instance, we're doing a plus b plus c, and if we added a plus b first and we took that modulo 12 and added c and did everything modulo 12, that's pretty easy to see. You get the same thing as if you did b and c first modulo 12 and then added a and took the result modulo 12. That proves associativity. That's the hardest one to prove. And then the only other ones we have to prove are identity and inverse. Identity is obvious. 0 is the identity element, because it's the identity element of ordinary addition. And taking a modulo 12 doesn't change that fact. So it's pretty easy to see that the element 0, if you add it to any other element, any other integer mod 12, you get that integer back. So the last thing we have to check is the inverse. Inverse is a little tricky, but it's not too bad. If you kind of look at the Cayley table, you can check for yourself. You can actually compute the inverse of any element just by looking at its Cayley table. For instance, if you wanted the inverse of 4 mod 12, what you could do is you could look for the 0 in the row corresponding to 4 and then see what column that belongs to. And I think you see it belongs to column 8, which means that 8 is the additive inverse of 4 modulo 12. There's actually another way you can do this. You can do minus 4 modulo 12. Just you can do 12 minus 4. Maybe that's the easiest way to do it. So to get the additive inverse of any element, any number from 0 to 11, just subtract 12 from that number, see what you get. Or set that number from 12. So, for instance, 12 minus 11 is 1, so 1's the additive inverse of 11. 12 minus 5 is 7, so 7's the additive inverse of 5. I guess the only exception is 0. You don't subtract 12 from 0, because that would give you 12, but you get 0. 0 is its own inverse. It's the identity. So that proves all the axioms of group theory. That proves that addition modulo 12 is a group. And not just addition modulo 12, but addition modulo any modulus. And I guess there's just one more thing I want to say in this lesson. I know this is probably hard for you to read, but here I'm just talking about isomorphism. So like I was saying earlier, I think I mentioned this yesterday, there's different groups that are isomorphic. They can be isomorphic to each other. And remember, yesterday I was talking about how we could also represent the cyclic groups C12 as powers of a squared, a cubed, up to 8 11th. Well, I think it's pretty easy to see that this group is isomorphic. This is a multiplicative group. So for instance, a to the 5th times a to the 8th would be a to the 13th, which is the same as a. And similarly, 5 plus 8 modulo 12 gives you 1, which you can see either from the Cayley table. And by the way, I didn't really show you how to use the Cayley table. Well, it's pretty obvious. You take row 5, column 8, see where they intersect, and they intersect in 1. So 5 plus 8 is equal to 1 mod 12. And so I think you see that these two groups are isomorphic. And we usually talk about isomorphism class as a group, so we just call both of these groups C12. And like I said earlier, there's nothing special about 12, the modulus 12. You can use any modulus you want. I give the example of 100. I think it's pretty easy to add modulo 100. You just take the last 2 digits of your result. That's the same. So for instance, 73 plus 38 If you did ordinary addition, you would get 111, but then you just chop off the leading 1 because you're only interested in the last 2 digits, so that would be 11. So 73 plus 38 is equal to 11 modulo 100 mod 100. So anyway, that's modular addition. Pretty straightforward. I think that's a very useful type of cyclic group. So that completes my video for today on modular addition. Thank you for watching. Long live math, and I'll see you guys next time. Bye.